This project is the design of a paraxylene production plant. We are Team 8. My name is Rachel Stiller. My teammates' names are Abraham Moshkovitz, Alexander Weisbeck, Rosa Garcia, and Alec Altman. This project was performed for ChE 470 as a part of the chemical engineering curriculum at Penn State. This presentation focuses on the design, economics, and feasibility of the xylene plant. The location and plant capacity details, as well as an introduction to the plant, will be discussed first. Following that will be an overview of the products and design of the process. Lastly, economics and future recommendations based on the feasibility of the process will be discussed. The xylene plant is built in Knitline Chemicals' existing Gulf Coast complex located in Houston, Texas. The plant capacity is 86 million pounds per year. The capital costs for the paraxylene plant are $82 million. The startup date for this plant is expected to be January of 2023, producing a desired paraxylene product as well as ortho and metaxylenes and benzene. The target after-tax rate of return is 15%, but because we were not making a profit, this value was incalculable. The net present worth at 15 years is negative $346.3 million. The xylene plant produces valuable paraxylene as well as ortho and metaxylenes and benzene. The main reaction taking place to produce mixed xylenes is toluene disproportionation. In this reaction, the toluene feedstock of 55,000 pounds per hour is converted into mixed xylenes and benzene. Two side reactions that take place in the reactor are toluene hydroalkylation and xylene disproportionation. These side reactions produce undesired benzene and trimethylbenzene. In order to rid of these undesirable products and to separate paraxylene from the mixed xylenes, a Parex separator was used. All other undesirable byproducts were separated by distillation columns. According to market data, the compound annual growth rate is 10.5% for paraxylene over the forecast period of 2018 to 2023 and will continue to grow for the use in polyester manufacturing industry.
All hard specifications and most of the soft specifications are being met. The only hard specification for this project was to achieve a 99.9% purity of the product streams. For example, our products for this project are paraxylene and benzene. The benzene product stream is currently achieve a product purity of 99.9%, and the paraxylene product stream is at 99.96%. There were a lot of soft specifications for this project. Some of them included in this presentation are stream composition and reactor pressure, that these soft specs will help prevent coating for the catalyst in the reactor. In stream compositions, there was a soft spec requirement to achieve a molar ratio of hydrogen and toluene of 2 and a hydrogen partial pressure in the reactor of 250 psi. One of the soft specifications that is not currently being met is product losses of benzene, toluene, and paraxylene across the plant. The major sources of these errors are the toluene purge stream that is currently set at 30% and the vapor distillate in the benzene distillation column due to a partial vapor and liquid condenser. Flammability and health hazards pose major safety issues. All of the chemicals used across the plant are flammable. For example, according to the National Protection Fire Agency, hydrogen is rated at number 4 on the flammability scale, as you can see in the fire diamond diagram. The plant uses organic compounds, for example, toluene, benzene, and paraxylene, which are rated between 2 and 3 in their respective fire diamond pictogram. This is a major concern because of the high pressures, high temperatures used across the plant. For example, 750 Fahrenheit in the reactor, and heat exchangers and distillation columns who operate above 300 Fahrenheit. Also, chemicals used in the plant pose a major health hazard. All of the chemicals used are irritants, which depending on the exposure time and exposure concentration, can lead to organ damage or tissue damage. Additionally, benzene, one of the major chemicals used in the plant, is carcinogenic. This is a main concern for employees who can be in direct contact with chemicals, for example, operators and engineers. This is of great concern because proper protective personal equipment and process control systems in the equipment have to be properly installed to avoid any catastrophic events.
So, hello, my name is Alex Weisbeck, and I'm going to talk to you about the BFD for our process. So we required 6 unit operations to convert and purify all of our process components. So we have a hydrogen and methane feed that mixes with the hydrogen recycle along with the toluene and benzene feed that mixes with the toluene recycle. That enters our packed bed reactor at 750 Fahrenheit and 400 psi, high temperature and high pressure, where our main paraxylene conversion occurs. After this, the reactor effluent goes to a flash separator where hydrogen and methane is taken out of the process stream and recycled back into the hydrogen feed, and some of the hydrogen and methane is lost to waste. The process stream then goes to the benzene distillation column, where the distillate is collected as a benzene product liquid, and then we lose some benzene product due to vapor. This process stream is then sent to the toluene distillation column, where we purify toluene and it is recycled back into the toluene feed. Some of the toluene is lost due to recycle. Then we go to the TMB distillation column, where our bottoms product of TMB is purified and taken out of the process. So then finally we have the Parex absorption, where our paraxylene product purity is met at 99.9%, and also our mixed xylene product is met at 99.9%.
Hi, my name is Rosa Garcia, and upon economic analysis, we found that the total plant cost was estimated to be $82 million. Upon the $82 million, the inner battery limit accounts for 51% of the total capital. The inner battery limit consists of the reactor, the flash separator, the benzene tower, the toluene tower, the TMB tower, and the Parex tower. Parex is the most expensive, but it's price dependent on flow rate. The reactor is operating at a high temperature and high pressure, and these operating conditions highly affect costs. The towers are relatively inexpensive, with benzene being the largest and the toluene, and lastly, TMB. The escalation and contingency are about a quarter of the capital. The only way to reduce this cost would be to rush construction, which would not be a good idea. There is no way to change the project contingency. Total OBL takes account in the site development, utilities, environmental impact, and raw material and storage. Startup, team costs, and other miscellaneous costs account for about 10% of the total capital. The total cash cost exceeds the profit for the paraxylene plant. The capacity of the plant was at 86 million pounds per year. The total cash cost of the plant was 126 cents per paraxylene pound. The cost of the total raw materials accounts for a large portion of the total cash cost. Cash costs must be below sale price of paraxylene to create a revenue.
Close it. Hi, my name is Alec Altman, and I'll be running you through some of the economics involved with our plant. So currently, the market price for paraxylene is 48.3 cents per pound. At this rate, the paraxylene product of our plant capacity is not economically viable, and for our plant design that currently exists to succeed, we would need the market price to increase. At our current rate, this would lead, after the 15 years of operation, we would have a net present worth of negative $340 million. If we were to artificially increase the market price to 146.7 cents per pound of paraxylene, we would be able to accomplish a 12% after-tax rate of return, which would, after 15 years of operation, allow our plant to break dead even and not lose or gain any money on the system. The target for this project was to reach a 15% after-tax rate of return, which at our current design would require 150.5 cents per pound of paraxylene. This would allow us to reach that goal and would give us a net present worth at the end of the operation of 15 years of $14 million. As part of our economic summary, we ran some sensitivity analyses to see how our plant would run under different operating capacities and conditions and see how stable our plant could be. For one particular analysis, we turned the capacity of our plant down to 90% and actually saw a net gain in net present worth of up to 11%. This is unusual, but because our plant currently runs at a deficit, this makes sense that running at a lower capacity would actually cause us to lose less money over the 15 years. So the flow rates of our product and feed rate streams are shown in the slides here, and we can see that the total cash cost actually increases, which is standard as you decrease capacity, but the net present worth actually increases due to burning less money. We can see that the base design has a negative $346 million net present worth, while decreasing it to 90% capacity has a negative $313 million net present worth. And again, that's an 11% increase. We also ran some alternate design studies to determine ways to improve the current process and how for future projects. We determined that purifying the toluene purge stream, which is currently 30% of toluene leaving the distillation column, so we have a 70% recycle, would actually add approximately $48 million per year of revenue to our plant. This is calculated by taking the amount of toluene that's being wasted, purifying that to a saleable amount, and subtracting that amount, which is $49 million located here, and subtracting that amount from the revenue lost from burning the waste stream, which currently under base design we gain about $700,000 per year from burning that stream. The trade-off for this change would be adding one new toluene distillation tower, which, including heat exchangers and pumps, would have approximately a $2.4 million capital cost up front. But overall, this is greatly worth it and would vastly increase the economic feasibility of our plant.
So finally, purifying waste streams with additional units could improve our economics. So firstly, if we increased our toluene recycle, instead of purging 30% like we do now and recycled 100%, this would add more toluene to the reactor and in turn convert into more paraxylene. Also, further purifying toluene and TMB products into saleable purities would increase saleable products and profit. And finally, adding a hydrogen purification via a P-swing absorption would allow us to purify methane from the hydrogen stream and allow us to sell the methane as fuel gas. And thank you.